Trees are extremely important data structures in computer science because if you're able to represent your data as a tree, you can often perform algorithmic operations more efficiently. Examples of trees are the file system on your computer with nested folders, or the DOM, in which you have a hierarchical structure in both. In this video, we'll explore exactly what a tree is and look at a few of the main different types of trees used in data structure and algorithm questions. Trees are a type of graph structure which start at a root node, which are connected to other nodes via a downward directed edge, where each node only has one parent. Let's take a look at an example of a tree. So here we have the root node, and let's just assign it a value of 1, although it's arbitrary. And then we have a second node here. And then let's say that also has a third node connected to it. And then we have a fourth node here, let's say. Then we have a fifth node here. And then we could have a sixth node here. And we could have a seventh node here, for example. So as mentioned, the first node, that's what's known as the root node. And this tree is this is what's known as a binary tree. So a binary tree is where each node, it can have at most 2 children. So if you look at this node 1 here, you can see it has the children 2 and the children 5. So there's just 2 children. And then each of their subnodes have at most 2 children here. So you could get an example here where there was one extra node here, 8. And that's all well and good because it still has less than 2 nodes. So that would still be a binary tree. It's possible that you can have a ternary tree. So let's just have a look at this part here. A ternary tree is just, it follows the same, it adheres to the same rules as a binary tree, but rather than having 2 nodes as children, it can have up to 3 nodes as the children. So that would be a ternary tree. And then if your node has more than 3, let's say it has 4, that's known as a n-array or n-array tree, where n represents the number of nodes. So that'll be 4-array, for example. So let's just undo that. There's a couple of other different types of trees I want to discuss. So we just talked about the binary tree, the ternary tree, and the n-array tree. You also have a binary search tree. And a binary search tree is where all of the child nodes are less than or equal to the parent. And the right subtree, all of the child nodes are greater. So for example, we have the number 3 here. That means to the left of that, we need a number smaller than 3. So let's just say that's 2. And then to the right, we have a number that's greater than 3. So that's 4, for example. And then this can continue on for as long as it can. And if it adheres to that sort of rule, then it will adhere to being a binary search tree. And then you also have what's known as a heap, and there's 2 different types of heap trees. There's the min and then there's the max heap tree. So let's just start with the max heap tree. So that's where the largest number's at the top. So let's say we have the number 10 at the top here. And then below that, all nodes below it must be recursively smaller. So this could be 9, for example, and then this could be 8, for example. This could be 7, and so on. This couldn't be a number like 17 or something. And so that's the max heap tree. You also have a min heap tree, which is the exact opposite, where the minimum numbers at the top, and then you can only have larger numbers below that. So for example, something like this, or something that actually looks like this on the left there, that happens to be a min heap tree. But I want to take a look at this binary tree in particular, because we need to know about some of the terminology associated with trees. So the first thing to note is each thing's obviously called a node, and the root node, or the first node, is what's known as the root node. You can also have a leaf. So a leaf is any one of these last nodes. So a child node, which doesn't have any further children. So when we say children, this first node here, if that's the parent, then 2 and 5, they're children of 1, and then 3 and 4, they're children of 2. So 2 is 3 and 4's parent. 3 and 4 has the grandparent 1. 1 has the grandchild 3 and 4. 3 and 4, they're related to each other because they're siblings of one another. And another way people call these sorts of things is, if you're on the node 3, for example, you can refer to anything above 3 on the same track here as an ancestor. So up until the root node, you follow from the leaf up the paths up to the root node. They'll give you, that can be an ancestor, and likewise for anything less, well, 1 has descendants of everything. If you take a look at 2, 3 and 4, they're children of 2, but they're also descendants of 2. So usually you just say parent or child, or sometimes grandparent and grandchild. But if it's more than 2 levels, sometimes you just say ancestor or descendant, or what level you're on. So that brings me to the point of the level. So this first level where you have the root node, this is a special case because it's the root node. So we say that that is level 1. Level 0. And then every level after that, you just add 1. So when I say level 1, this is referring to the height of this here. So this is level 1, and this is level 2, for example. So you might also have the height that you need to know. So the height of the tree is simply the height from the root. So the height is simply the number of edges in the longest path from the node to the leaf. So for this root node, for example, we can see that there's one edge here and another edge here. So that means the height of the tree is 2, and also the height, so the height of this node 1 would be 3. So if I was considering this node 5 here, we would say that that has a height of 1 because there's one edge between the root and the particular node that you're on. There's also what's known as the depth, which is basically the opposite. So the depth, it starts at 0. So the depth is the number of edges in the path from the root to that node. So looking at it the other way around, the depth here, so that's the level. I'm going to put D here for depth. This depth here of the first, it's the number of edges in the path from the root to the node. So obviously we're already at the root, so it has a depth of 0. But then here we see that we've got a depth of 1, so there's one edge from here. And then we also have a depth of 2 here. So we've got the level. So the depth is the same as the level essentially, but then you've also got the height. So I'll put H here. So sorry, the depth isn't the opposite of the level. It's the same as the level. It's just another word for it. But the height, that's going to be the opposite. So the height here, this is the number of edges from the longest path to the node to the leaf. So, you know, if we're considering this root node, we see that this has a height of 2 because the number of edges in the longest path from this node to its leaf has 2 edges. And then let's say I'm on number 5 here, we see that, you know, there's only one path below it, or one edge to get to the lowest one. So that would be 1, and then here there's nothing below it, so there's no edges below it. So the height's just going to be 0 there. So this is a binary tree. And as you can imagine, you have this many number of elements, so you're going to need O of n space to be able to store it. And if you need to traverse through all of the elements or all of the nodes, that's going to be O of n as well. But in this particular case, you can see that we have a balanced binary tree. So I'll go into details about that in a second, but basically what it means is if you have your tree structured like this and your data is structured like in this format, basically an array in a certain order, you can actually do things where you can split this in half. So this is sort of like builds up on the logarithm video which I talked about. So if you haven't seen the logarithm video, check that out. But if you can split this in half and get rid of half of the elements, and then I can get rid of half of the elements again, effectively, rather than traversing things in O of n, you can do it in log of n times. So, and that's true if things are balanced. So this leads us to the question, well, what is balanced? And it's the opposite of skewed. So see how we got the numbers 1, 2, 3, 4, that. You could have the case where you have a tree that looks more like this. So you'd have the number 1, 2, 3, 4, 5, 6, 7. And then all of those would connect to one another all the way down here. So that means like the height of the tree is much larger than it is here. So basically, you can say that a tree is balanced, you know, if you're able to traverse things such that you can continually split things in half each time, or that's known as log of n. So when we look at the branch is the start. We start at the root node, and then we make our way all the way to the child here. So, or the leaf, and that's what a branch is. So, you know, this whole thing here, this is a branch. You know, this part here is a branch, basically traversing from the root to a leaf. That's a branch. So what we can say is we can say that, well, there's some other terminology to know. There is having the tree being complete or not. So the tree is complete if every level is filled left to right, but you can have some last nodes free. So for example, if you had 1 here, and then rather than pointing to a left node, you pointed to a right node here, or let's say you had another level, you have 2 and 3, and there was no left node of 2, but there was a right node of 2, this wouldn't be complete, because in order it to be complete, each level needs to be filled left from right. So that means even if you had something like this, 1, 2, 3, 4, in the case of a binary tree, that wouldn't be complete because, you know, things like this cell here isn't filled out, for example, or that node there. So there's also the notion of a tree being full. And a tree is full if each node has, in this case, both of its children. So we can see here that 3 and 4, they're both there. So, you know, if we're considering this tree here, and if you consider a tree at a different node from the root, that's what's known as a subtree. So if you consider this subtree here, we can see that this is full because, you know, the node, it has both of its children. And then it's also full because even though 3 and 4 don't have children, it doesn't have any children. So if it had 1 children, that wouldn't be complete. Oh, sorry, full. It would be complete. And then we can say a tree is perfect if it's complete and full. So a tree is perfect. This is a binary tree. This is perfect. So basically it's complete, meaning every level's filled from left to right. And then also it's full. So it either has both its children or no children. So here at level 2 and 5, we see it has both its children. And then at this level, it has no children. And this concept extends to ternary trees and annary trees because you just sort of got to extend the number of nodes of the children. So for example, if this is a ternary, you know, and we're just considering this subtree here, we would say that this tree is complete, or this subtree is complete because it's filled left to right. But if this one wasn't here, then it wouldn't be complete. And it's also full because 5 has all of its potential children spots taken. So all 3, and then these ones have none. So there's no stuff like this going on. So this would also be perfect. So that's what I really wanted to talk about trees. In the next video, we'll actually start to explore some algorithms, so binary search, and looking at all sorts of binary trees and other types of trees, and actually doing some algorithms of these. And you're going to find that these are actually extremely useful in your everyday programming, and they come up quite a bit in algorithm questions.